Throughout the course so far, when we've seen situations that involve multiple force vectors, we've already gotten in the habit of drawing simple diagrams to represent them. And specifically, anytime we draw a diagram where all of those force vectors are as if they're lined up tip to tail, stemming from the center of that object, what we've really drawn is a special kind of physics diagram. It's called a free body diagram. The free body part means that it's just a single object with nothing around it, and we're just representing the forces on that one specific object. And it, in the long run, can help us to figure out what the total or the net force on that object is actually equal to. In general, in your note, I'm going to encourage you guys to use straight lines, so please use a ruler. It's a little bit tricky for me to do that on the smartboard here, even using the line tools. So I'm just going to be doing mine freehand, but try to do yours much neater than mine. Just to give you an example, though, of what a free body diagram might look like, let's say we have a simple situation of a box, and draw some point in the middle of it that represents where all the forces will stem from in that case. And so this box, of course, is feeling gravity pull it down. But if it's not going through the floor, it's also feeling normal force pushing it back up. In this case, though, let's imagine that it's also being pulled with some applied force. But even while that happens, it would still experience a little bit of frictional force, which would be going back in the opposite direction. So that's a simple case of a free body diagram, and we might also want to be a little bit more specific. Anytime we recognize that there are forces that are equal to one another, we can use that trick that I showed in a previous note and insert some little dashes or tick marks on those lines, because we know in this case gravitational force will be equal to normal force, and that's why it's not accelerating up or down. But in general, when your forces are not all in balance, we have some overall net force. And specifically, when there's a net force, objects will accelerate in that direction. It's not just that they'll move in that direction, they'll actually accelerate. They will speed up in the direction of their net force. And so in this case, we've already talked about how the gravitational force and the normal force cancel each other out. They're equal and opposite. But we have some amount of frictional force and some amount of applied force. But because the applied force is the much greater force, the net force overall, or the total force, would be more so pointing in the right-hand direction, which means this object would actually be accelerating towards the right if this were the free body diagram that was truly associated with it. For our first attempt to draw a proper free body diagram for a specific situation, we'll keep it really simple to start with. So we'll just take the situation of dropping a rock. And so in this case, if it's something really simple to draw, like a rock, you can draw something that kind of looks like a rock. But it doesn't have to look like the object at all. In fact, for most free body diagrams that we do, I'm just going to draw boxes to represent the object. Because as I mentioned with our horse discussion in our previous lesson, I have terrible art skills. And that's totally okay, because it didn't matter what the actual horse looked like. It doesn't matter what these objects in general look like at all. If we just mark off some point roughly in the middle of that object that all the forces will stem from, we can draw the rest of our forces from there, and it doesn't actually matter what the object looks like. So this rock is fine, but we know that if it's dropped, it's feeling the force of gravity. So there's really only one vector that we need to draw. Fg, it's the force of gravity pulling it down. Now, in reality, when something falls, it does actually feel air resistance as well. But we'll talk about air resistance in class a little bit and the details behind it a little later on. For now, let's just assume it's only feeling that force pulling it down. So if that's the only force that it's feeling, that means that's also its total force that it's feeling. So the direction of its net force, or its total force, is down. And then we know that the rock will also be accelerating downwards because that's what gravity does to things. It makes them accelerate downwards at 9.8 meters per second squared. So we can answer this question with a resounding yes. It is accelerating in the same direction as its net force. That's what the general rule throughout this entire unit will be. That if there is a net force that's in a particular direction, as long as it's not zero net force, the object will accelerate in the direction of that net force. But now let's try a little bit more complicated example. And this example is actually very similar to the one that I sketched out at the very top of the note. But now we're just going to put a little bit more specific information into it. We've got a box that's sliding across a table. So let's just draw our box. And again, it's a free body diagram, meaning we just need to focus on the box. It doesn't matter any objects that are around it. The table itself that it's sitting on doesn't really matter. We're just going to focus on the specific object itself, just the box. And so it has gravity, of course, trying to pull it down. But it's not accelerating through the table. It's not getting pulled right through the table by gravity, and that's because, as we discussed before, there's some normal force pushing it back up from the table. And specifically, just like we saw in our normal force note, we know that if it's not getting pulled through the table, that means those must be perfectly balanced with one another. All of the force that gravity is pulling down with is being canceled out by the normal force pushing up with an equal amount. But there are some horizontal forces as well. So it's being pushed across the table with 30 newtons of force. So I'm going to call that FA. And it's 30 newtons in this case specifically. It's feeling a lot of friction, but it won't quite be as much as the applied force. So I'll draw a vector that's not quite as long and call that friction and label that as well. It's 25 newtons. And so this is my overall picture of what's going on. I've now labeled all of the key forces involved. Now I need to ask myself, what direction is the net force in? Well, in terms of looking at net force, we know that the Fg and the Fn essentially cancel one another out. They won't affect our total. They equal zero net force when we combine them together. It's the other two that we need to think about. But because the Fa, the applied force, is greater than our frictional force, we know it's going to accelerate in that same direction. So specifically in our case, we could say that it is going to accelerate to the right. Well, we should say first that the net force is to the right, and the box will accelerate also to the right. That little follow-up question, why isn't the box accelerating up or down, is something that I want you to think a little bit about, and we'll talk more about in class. And as I've mentioned, sometimes forces are balanced, meaning that one force might be completely canceled out by another force going in the opposite direction. And sometimes all of the forces on an entire object might be completely balanced, so every force that it feels is completely canceled out by some other force. In that case, when all of those forces are balanced, an object will remain at rest, or if it was already in motion at the time, then whatever velocity it had, it won't accelerate from that. So if it was actually in motion, it will just remain at that same constant velocity. And that's important. So it's not necessarily that the object won't move, because it is possible for an object to be moving even when all of its forces are balanced, as long as it's not accelerating. When we have unbalanced forces, it causes objects to accelerate. But they still may be in motion, even if the forces are balanced. It just means they'll go at a constant velocity. A good example of balanced forces is to just picture, as it says there, a game of tug of war. Imagine what's happening with the center of that rope. at the center of that rope, if those two teams are pulling with equal amounts of force, the center of that rope won't move at all. That's essentially what's happening to objects that are experiencing balanced forces. So let's try a little variation on our last example. What about if we're pushing a block, just like we were before, across a table, but now we're pushing it at a steady speed, meaning a constant speed. So you can maybe even add that to your note if you think you'll forget what I mean by steady. It's just constant. And so if I apply or exert a steady force, again, meaning my force amount that I apply to it won't change, why isn't it accelerating even though I'm applying all this force to it? Well, let's take a look at what its free body diagram would be doing. So I draw my box, and I've got gravity still going down. I've got normal force still pushing up, and they balance each other out and cancel so that it's not accelerating through the table or jumping up in the air either. But we know it's being pushed with some applied force. Now, just for clarity, I know that force that I just drew, just like I did in the previous example, looks like I'm drawing a rope that's being pulled. But in this case, I am still representing the object being pushed, even when I draw the vector coming out from it. So I'm always drawing the vectors coming out from the center, even if it's representing a push. And I know in this case it does look more like a pull, but I'm always just drawing them as coming from the center of the object. So that's my applied force. But then I always know that anything that's sliding along a surface is also feeling some frictional force as well. And I did my best to draw that fairly similar in length. And that's important because when we try and figure out why this isn't accelerating, we need to think about balanced forces. If something is moving at a steady or a constant speed, that means all of its forces must be balanced. So if there's an applied force, it must be equal to the frictional force in this case. So I'm actually going to add two little tick marks to both of them, because what we're also seeing is that whatever the applied force is, the frictional force must be equal to it to completely cancel it out. So for your notes, we can just write down that we've recognized that it's constant speed, and what that means is that we have balanced forces. So how did we get these balanced forces? Well, more specifically, just to write it as a math statement, we can say, therefore, we know that FA, whatever applied force I'm pushing with, must be the exact equivalent to however much frictional force I'm feeling as it slides. And let's try one final variation on the block situation. So imagine I push a block with one quick push, but then I just let it slide to a stop. I want to draw an FBD of the block sliding. And careful of the language there. I'm not going to draw anything about when it got pushed. I'm just going to draw the block as it's sliding after I've pushed it. And let's think about what that would look like. So I have my box, once again. It still feels the force of gravity pulling it down. We can't forget about that. But the reason it's not going through the surface is because it's feeling normal force pushing it back up. It's not accelerating at all, up or down, so we know that those must be equal to each other. But what other forces are there? Well, we're not pushing the block anymore because we're just going to look at when it's sliding after I've pushed it. But if it's sliding along the surface, let's say that it's moving in this direction. So that's the velocity that it's going in. We can draw the frictional force going back in the opposite direction to the direction of motion. Because remember, it's a resistance force. It's always trying to work against whatever motion is occurring. So the velocity is going that way, but the friction is going the opposite way. Well, let's analyze this. What direction is the net force actually going in? Well, in this case, specifically, we haven't really labeled it as north, south, east, west or anything like that, but we'll say backwards. So what is that telling us? It's telling us that therefore the acceleration is backwards as well. So what does that mean? An acceleration that's in the backwards direction? Well, specifically it means that the object is slowing down. We've seen this before, that any time your acceleration happens to be in the opposite direction to your direction of motion, it causes something to actually decelerate. It becomes what we would call a negative acceleration, and it slows down in that case. So we've seen a few situations. In some cases, an object might have a net force in its forwards direction and it'll speed up. Maybe it has zero net force and all of the forces are completely balanced, and in that case it'll either stay at rest or stay moving at a constant velocity. Or it might feel a net force in the opposite direction to what it's moving in, and in that case the object will decelerate. It'll still experience what in physics we would call an acceleration, but it would technically be a negative acceleration, which we would call a deceleration in our more common language. The last two examples in the note I want you to think about a little bit on your own. You can try them for yourself, but we're going to take them up in a little more detail in class and fill in and answer some of the other little detail questions that have come up along the way.